Hey everyone, today we continue on to value iteration. So in the previous RL video, we took a look at policy iteration. And so now it's time to do value iteration, which is the second form of the model-based reinforcement learning that we're going to be looking at. So if you didn't look at my policy iteration video already, then this won't make all that much sense. So I'd recommend just go take a look at that first and then come back here afterwards. So let's remind ourselves exactly what's going on. When we solved for the Bellman equation, so in one of my previous videos, we did a full derivation of the Bellman equation. Again, go take a look at that if that's interesting to you. But when we solved for the Bellman equation, there was a couple of small details that I wanted us to keep in mind. To solve our Bellman equation, the original Bellman equation, it requires us to have the policy pi, which is basically prescribes what action should I take at a specific state. It requires us to have the policy ahead of time. And so this leads to a couple of problems. Namely, the policy is what I want. In the end, once I'm done training my model, what I want is the policy. What action should I take at every state is exactly the question we're trying to answer with reinforcement learning. So the Bellman equation requires us to have something that we want, which doesn't really make sense. And so to solve it, we used a method called policy iteration. Then in a future video, we looked at the Bellman optimality equations, which is essentially just a approximation of the Bellman equation. And it is it's a valid optimal solution of the original Bellman equation, which we again took a look in that video. So again, go take a look at my Bellman optimality video if you don't know what that is. But we briefly showed that instead of just averaging, because this is an expectation equation because we're taking a weighted average over the policy over all of this stuff here. And all of this stuff was basically our Q values for some specific state and action. Instead of doing that, let's iterate our values, basically iteratively solve for them. And in every iteration, just select the action that gives me the maximum Q value, right? So again, for every state action pair. So select the action that maximizes my future expected rewards for that specific action. And that was the key idea behind the optimality equations. And again, the proof behind why this is optimal is a little bit more challenging. We didn't go into too much detail there. It has to do with the Banach fixed point theorem and a couple of other stuff. But regardless, we had two forms of the equation. And so using these two forms, we have two methods. Number one is the policy iteration method. In policy iteration, go ahead and start with a random policy, right? Start with a random policy. And then for that specific policy, do a method called policy evaluation, where we evaluate what are the values of that policy. So that's me applying this Bellman equation, compute the values for this specific iteration of my policy. And right now, my policy was just randomly initialized. Once we had done that, I now have my estimate of the values, right? Estimate of the values for this specific policy in my environment. So now I can use a method called policy improvement where I update my policy. And policy improvement was pretty straightforward. It was just select the action that maximized my future rewards given the kind of values that I already computed. And so that was essentially our way. We kind of had this iteration between randomly initialize the policy, compute the values, use the values of this current iteration to update the policy, improve it, and then use the improved policy and again compute the values. Use that, and then kind of just go back and forth. So it was this cycle of going back and forth, and that was really the only way we could leverage this Bellman equation, because the Bellman equation directly requires the policy. Now in the Bellman optimality equation, notice there's no policy in here, right? We have no pi in here anywhere, which means we now have an iterative approach to directly solve for the values. Find the best values for this specific environment, ignoring policy altogether. There is no policy. So we initialize the values as 0 and compute the optimal values for this specific game. Once we have computed the optimal values, then we can go ahead and derive the policy from those values. And deriving the policy from the values is basically the same as policy improvement. In policy improvement, we updated our policy based on the values, right? We picked the best policy based on our estimates of the values, the future rewards I expect to get. And so if that's the case, then we can again use policy improvement to just update our policy, or basically find the policy from our values. The only difference is there's no back and forth anymore. We iteratively compute the values, and once our values have converged, we compute the policy once and we're done. Whereas in the policy iteration method, we initialize a policy, compute the values, use the values to update the policy, use the policy to update the values, use the values to update the policy, and it's kind of this, we repeat this process over and over again. So this should be pretty straightforward. We'll be able to reuse a little bit of the code from last time. So let's go ahead and do it. Okay, so what are we going to need? We're going to need NumPy, import NumPy as NP, and import Gymnasium as gym. So again, just like before, we'll be using the frozen lake environment, and we're going to be jumping straight into the is slippery. So we're going to do a stochastic environment. Let's see here. Gymnasium not installed, so I have to do pip install Gymnasium. I could have forgotten to, there we go. All right, good. Could have forgotten to just do the right content environment, so we're good to go. So that is our Gymnasium environment. We opened up our frozen lake environment. We're doing a stochastic environment, so it's slippery. So if you take a step, if you want to move down, you may go left or right. It just, it's a random. And so if you're confused about any of this stuff, I go into the details of the frozen lake game and stuff like that in that previous video where we implemented policy iteration. So just go take a look at it there. And this was a quick helper function I wrote last time just to print out the policy in a nice way. And we'll kind of see that applied. It just makes it easier to interpret what we're looking at. So the important part is value iteration. That's what we're here to implement. So we're going to do def value iteration. And it's going to be our environment. We have to set some gamma. Let's do 0.99. That's our discount factor. We have how many iterations do we want to basically update for. Iterations is 1000, and this is the maximum number of iterations. Of course, if our values converge ahead of time, then we're just going to go ahead and cut it off, and we'll have some tolerance. Let's just set it to 1e minus 5. So if our values stop changing by that much, then we're done. We don't have to worry about it anymore. So like I mentioned, our first step is let's go ahead and initialize our values as zeros. So we're going to do np.zeros. Right, so we're going to set these as zeros, and it's going to be for the env.observation_space.n. Right, so what we're doing is just go ahead and how many states do I have? That's this, right? So we have, in this game, we'll have 16 possible locations we can be in. So we want to compute the values for all 16 locations. Right, so that's the key idea. And so let's go ahead and do for blank in range num iterations. So how many iterations of updating do we want to do? Let's go ahead and create a copy of our current value estimates, np.copy. Right now it's just zeros, but of course it'll update as we keep going. And this is so we can do our future reward. So again, remember in this formula, so we also have the optimality for the Q values. We're not going to be looking at that today. We're just looking at the values. So there we go. And so to compute our value of this iteration, we need the values of the previous iteration's estimate for the next state. So this V star here is the V star of the previous iteration. This V star here will be the V star of the new iteration. So a little bit, overuse in the notation, but that's just something to keep in mind. We use the previous estimate to update our new estimate, and the previous estimate is for our S prime, so it's for the next state. So we're just creating a copy of the current estimate of V of our values, so we can use it to update to the next one. So we're just creating a new copy of it, nothing crazy. So we created our copy, and now what we're going to do is we need to do this iterative approach for all the different states in our environment, right? Not just for one state, but for all of the state. We want the values of every single state. So let's go ahead and do that. For S in range env.observation_space.n. So we're going to loop through, in this case, there's 16 states, so index 0 through 15. And what we want to do is select whichever action maximizes this value. And if you again remember, this value here is just our Q value, right? This is just another way of writing the Q value. So what we need to do is check every single action, do this computation, and then select the action that gave the maximum future reward. And so that's the key idea. And so let's go ahead and implement that. Should be pretty straightforward. This is going to feel like a lot of what we did last time, right? So it should feel a little bit familiar. So we're going to do QS. So this is going to be the estimated value for this state, let's just say. And we're going to loop through all the actions I can take, and then we'll argmax it at the end. So there we go. We're going to first go ahead and just create an empty list where we're going to store our information. And we're going to do for wanted action in range env.actionspace.end. So these are all the actions I want to take. Now, again, remember, in the stochastic environment, sure, I might want to go right, but you might end up going up or down because of the randomness built into the frozen lake environment, because we set is slippery to true. So that means if you, again, I'm not going to recap too much of this right now, but let's just make sure we look env.unwrapped.p. We have for our state 0, so if we're in the first state, or the first location, our starting location, if we take action 0, right? So if I take action 0, which I believe was going left, I can't remember, but if we take action 0, that means, and that's left, yeah. So if we take action 0, there's a 33% chance I end up in the same location. And there's a 33% chance that I go somewhere else and a 33% chance I go somewhere else, right? So those are the options. So if I'm here, if I take a left, if I want to go left, I can either go up or I can go down. And if you're in the top left rectangle or top left location in your area, so we can just double check what it looks like. So if you're in this top left area, if I go left, I'm stuck in the same place. If I go up, I'm stuck in the same place. But if I go down, I'm in location 4 now, because it goes 0, 1, 2, 3, 4, right? So we can see these are all the options, all the places I could end up in given the action I want to take, because it's stochastic. Again, there's more details on this in that previous policy iteration video. But that means that, remember, this is a model-based method. We need to average over all the possible states I can go to, which is why we have this transition probability here, right? For what's the probability of getting to some state S prime, given I took some action at state S. So we need to sum over all of the possibilities. And so now we have this internal for loop as well. So sure, I wanted to take this action, great. But possible taken action. So what are all the things that could end up happening? That's env.unwrapped.p, right? That's my Markov decision process for this environment. I wanted for this state and for the wanted action. Like, sure, I wanted to take this action, but what are all the things that could end up happening? And we need to average over those. And so now we're going to create a QSA is 0, and we're going to accumulate in here for this state and for the action that I want to take, what is my expected future rewards, which means we need to just accumulate it all together. So we can do for, and let's kind of remind ourselves again, let's put that back, env.unwrapped.p, and let's say we're at state 0 and we want to go to the right, right? So let's say 2. I believe 2 is right. Yeah, 2 is right. So that'll show us something like this. We'll have a list of all the things that can end up happening. And this says that if I go right at state 0, there's a 33% chance I end up at state 4, a 33% chance I end up at state 1, and a 33% chance I end up at state 0. I get no reward for any of them, and all of them are false. So the game is not over. So this is all the information I need. So we're going to loop through that. We're going to do for probability, ability, S next, what's the next state I could end up in, reward, and terminal is the game over, in possible taken actions. We're going to do QSA plus equals, and we're just going to follow the formula, right? It's going to be the probability, right? The probability of this transition happening, in our case, it's all 1/3, times the reward I get for taking that action, plus discounted future rewards, where future rewards are represented by our current estimate of what that value is. So let's go ahead and do that. It's going to be QSA plus equals probability times reward plus gamma times our current estimate, VK, of the next state. Just like that. So now that we have that, we're going to go ahead and store in our QS. So now that we've accumulated all that information together, in our QS, we're just going to go ahead and store our QSA. There we go. And then once we've repeated this for all the possible actions I could have taken that I wanted to take, I can then go ahead and store for my values for this specific state. I'm going to store np.argmaxqs because it's by index, right? So it's going to be either I take action 0, action 1, action 2, or action 3, right? Those are my 4 available actions at this date. So I have 0, 1, 2, 3. And I'm just going to go ahead and store in my values np.argmax QS, right? Go ahead and store that information. Oh, actually, wrong thing. np.max. We don't want to store the we don't want to store which action is maximum. We want to store the maximum value. So whatever is the maximum Q value is what we're going to store in there. So we're going to select the action that maximizes this. So we just do a max, not an argmax. So sorry, small mistake, but there we go. We now have our values. And then lastly, we're going to do if np.max, np.abs. We're going to just check between our current estimate of the values minus, or I guess v is now our updated estimate of the values. And we're going to do our previous estimate of the values. And if the maximum absolute difference is less than our tolerance, then we can go ahead and break and we are done. We can return v. So that's basically it. This is value iteration, which will compute what are the best values, or basically the optimal values for this specific MDP. And so we can then go ahead and run, hopefully this all works, optimal values is equal to value iteration, and we just pass in our environment, right? Because that's what we passed in here. I'll leave everything else as a default. And so then we can go ahead and print, let's go ahead and print np.array optimal values, because right now our v that we returned here is just a, well, it's still an array, so I guess it's fine. Yeah, okay, we didn't really need the array, so we can get rid of that. The optimal values is an array, but we're going to reshape it, reshape to 4x4, right? So we're going to make it a grid, and these are our optimal values for our entire setup, right? That's our optimal values for this specific game. So we're good to go here. Now that we have our optimal values, we need to derive our policy from these optimal values. That's the key part. And so this is what we had done last time. This is the policy improvement step. Select the action, so now it's an argmax. So select the action that maximizes my future Q values, right? So take the action that maximizes my future Q values. So let's go ahead and do that. We already wrote this code last time, so we're just going to write it again for anyone that's new here. But again, I would definitely recommend you go ahead and take a look at some of the previous videos, because these are going to be pretty cumulative as I'm going, because I don't want to rewrite too much code, but this one's pretty easy. So we're going to take in these values and we're going to derive our policy from it. So we're going to do new policy. It's going to be np, let's just initialize them as just an empty list of zeros, and we'll fill them in one state at a time. Observation space dot n. There we go. That's our new policy. And we're going to do for s in range env.observation space.n. Right, so we're going to, for every single state, because we need to derive our policy for every single state. So there we go. For every single state, we're going to do basically what we had done earlier. What is the, it's going to be a lot of repeated code. It's exactly what we just did. What is the best action I can take? Well, let's go ahead and store a computer Q value for each of those actions. We're going to create this empty list again. And this is going to be exactly what we had done before. For wanted action in range env.action space. So what are all the actions I want to take or could take? And then we're going to do possible taken actions is env.unwrapped.p, again, for this state and for this wanted action. So no new code yet. This is, again, looking exactly like what we had done before, right? From this step. And actually, basically all this code is going to be identical, but I'll write it again anyway. And then for this specific state action pair, we're going to set it to 0 initially, and we're going to loop through all the possibilities, all the possible transitions I could have made, even though I intended to take that wanted action. So for probability, our next state, our reward, and is the game over, in possible taken actions, right? For all of these sets, we're going to store Q SA plus equals our probability times the reward I got for this action that I took at this date, plus gamma times my future reward. And in this case, notice we're going to use our values. We already have the estimate for the values. We have V star S prime. So we have our best values for this environment. So we can go ahead and use them and use it to find what is the value of the next state. So we're going to use our values, and then you do it for S next, right? The values of the next state. And then we're going to do qs.append qsa, right? Go ahead and store that there. And then our best action, and this is the difference, we're going to do an np.argmax qs. Oh, oops, deleted everything there, QS. So I want the action that gives me the maximum value. Earlier, we wanted the maximum value itself, right? So again, this is still find the action that gives you the maximum value, but what we want here is the value itself, right? The Q value. So there we go, we stored the value. But now what we want is the action itself. So I want what is the best action I can take because I'm deriving the policy, right? So the policy needs the action. And then our new policy, S, is going to be our best action. So we're going to go ahead and take this best action that we just derived for this specific state, and in our new policy, go ahead and store our action. And this really isn't even new policy, it's just the policy because we're not actually doing a policy improvement. So just to make it clear, we can just call it policy. It's not, there's no new, we're not iteratively solving for the policy like we had done earlier. It's just we solve the policy for once and we're done. And return our policy, which means now I can do my optimal policy is equal to policy improvement. But really it's just policy. It's not really policy improvement. We're deriving the policy from our values, but either way, optimal values. I think that's what I called it. Optimal values. Yep. And then we can use that method I wrote, print policy, and it just nicely prints it out for us. Optimal policy. And there we go. So this is the policy that we have decided to use. We decide to go left, up, right, whatever, right? So that's the policy. And what we want to check now is how does this do, right? Let's just go ahead and play a couple games. So let's play num games. There's 1,000. Let's play 1,000 games, and let's make the games a max of 500 steps, but nothing really goes that long. But either way, it's just a placeholder. We're going to do game successes is 0. And we're going to do for blank in range num games. What we're going to do is our observation, right? So start a new game. So observation, some other info we don't really care about is env.reset. It's going to start a brand new game. And we're going to do for blank in range max steps, right? So for 500 steps or earlier, if the game ends earlier, action is equal to int, let's make sure it's an int, optimal policy, right? So we're going to grab from our optimal policy our observation, which is what state are we currently at. So basically it's saying for this specific state, whatever state I'm at, I want the action that I assign for it. So that'd be at 0, I want to go left. At 3, I want to go up. At 15, I want to go or whatever. Basically, what is the action that I want to take at that state? Now that I have that, we can go ahead and actually take that action. So observation, reward, done, and it gives some extra information, but we're going to ignore it for now, is env.step, and we're going to actually perform this action in this environment. And if done, so if the game is over, and the game's over either because we can check, we either fell into one of the ice lakes, or we got to our present. Either one is a valid end. And if it's done, then we do if reward, right? So if reward greater than 0. Remember, in this game, you get a reward of 0 everywhere and a reward of 1 if you get to the present. So as long as we have a reward greater than 0, we have beat the game. We're going to do game successes plus equals 1. And so we are now done, and we can do game successes divided by num games. So how many games did we win? And we'll see that, let's let it play a bunch of games, and we can see we won about 83% of the games. And so that's it. That's essentially our value iteration. Nothing too crazy. It's just another way of solving the MDP. Again, as a recap, there's basically two ways. We have policy iteration and value iteration. Policy iteration uses the original Bellman expectation equation, and it does it by iterating between start with a random policy, derive its values, then using those values, update the policy, improve it. Once you have the updated policy, again, derive the new policy's values, and you just go back and forth until you've converged. Similarly, the value iteration uses the Bellman optimality equations, right? So a little bit different, but now just initialize the values as 0 and just iterate the values until you've computed the ideal values for this specific game. And then once you've updated all of the values, you're done, and you can go ahead and just derive the policy once from those optimal values. And deriving the policy here was exactly the same as doing the policy improvement, or just finding the best policy for those values that we saw in policy iteration. So that's basically it for our model-based learning. In the next RL video, we're going to start looking at model-free learning, which is going to be much more interesting because in the real world, you don't have a MDP that just describes the world to you. You have no idea. So now we need to start exploring the environment and getting good estimates of what's going on. And so this is going to be essentially us looking at some methods like Monte Carlo, and then we'll move on to like TD learning methods like SARSA and Q learning. And that will set the stage for us to start exploring our deep reinforcement learning. So as of now, we can actually go back here. We have officially completed the first block. Model-based is done. On next will be our model-free learning. So I will see y'all in the next one.